So people, question number 16 says that there is a satellite moving in an elliptical orbit around the Earth. The mass of the satellite is very small compared to the mass of the Earth. Which of the following statements is correct? Now again, more than one answers can be correct here. Let's look at the options and go one by one. Arnav?
Okay, see, the first option is the acceleration of S is always directed towards the center of the Earth. So this is actually the correct option, because whenever there is circular motion and there are spherical bodies and all,
Right.
the net force is in the direction of, let's take an example over here. Okay, this is an ellipse, this is the center over here, and this is the object with small mass m.
Right.
Okay, so the net force is in this direction. So therefore the acceleration vector will also be in this direction itself. So therefore option number A is correct. It will always be in the center.
Okay.
Now coming on to option number B, the angular momentum of S about the center of Earth changes in direction but remains constant in magnitude.
Right.
So the angular momentum of S is constant in direction, because see, whenever you take this torque, like R cross V, okay, velocity is over here, R is over here, so you always get it in coming out of the plane.
Right.
You always get it in this direction. Therefore the angular momentum changes in direction. This part is wrong. Okay, the direction of the angular momentum remains same. Therefore this option is incorrect. Now we come
what about the magnitude? Does it remain constant in magnitude?
It remains constant in magnitude. Yep, because mv into r. So I'll write it down.
Yeah.
The angular momentum will be mvr. So as the radius increases, the velocity will reduce. So therefore this total thing will be equal to constant. Or we can think of it from this point of view also, that the net change in torque is equal to change in net external torque is equal to change in angular momentum.
Okay.
The angular momentum upon time upon dt. Okay, so here there is no external torque, the only torque is internal, and this is also zero because it is passing through the center. So using this also we can find that the angular momentum will be constant.
Right.
The magnitude as well as the direction would be same, it won't change at all. Now the total mechanical energy of S remains constant. So the total mechanical energy will remain constant as it is changing. It is an elliptical orbit, so the linear potential energy, kinetic energy and linear momentum vary periodically. That is, they'll increase and then they'll decrease. Therefore option C is correct and D is incorrect.
Okay.
The linear momentum also remains constant. This is also incorrect because the velocity changes. So this is about it.
So guys, you have to pay extra attention when they're talking about elliptical orbits. Circular orbits are simple to calculate, and linear momentum and total mechanical energy remain constant in those cases.
Whereas, that is
elliptical
correct.
cases,
it changes. They vary periodically.
You can actually go through the options of this and remember this for the future.
Yeah, and this is a JEE question.
Good. So we'll move on to the next question now. Now in question number 17, we have a uniform sphere of mass m and radius r, which exerts a force F in a small mass situated at a distance of 2r from the center O of the sphere. A spherical portion of the diameter r is cut from sphere as shown here in this figure. The force of attraction between the remaining part of the sphere and the mass m will be what? Arnav?
Okay, see. So first of all, in a cavity question, we have to find the density and we have to find the mass of the small cavity and all. So I'll write down the mass relations first. Rho is equivalent to mass upon volume.
Right.
So therefore, using this, we can get the initial mass of the whole thing as rho into 4 upon 3 pi r cube. And the mass of the cavity, I'll write it as m2. Okay. Rho into 4 upon 3 into pi. This is r by 2, so r cube upon 8. This will be equivalent to m1 upon 8. Okay. So I've just written them down. Now we'll solve the question. So initially, when the cavity was complete, the gravitational force would have been g m1 of course upon 4r square, because the distance between them is 2r. Okay. So this is the initial force. Now what happens is that we cut a cavity. So how to solve this question? See, to solve this question, you have to think of the cavity, that the cavity is exerting a negative gravitational field. So that when it's the negative of the cavity and the positive of the sphere, like it will cancel off. So totality would become 0 due to this. The contribution due to this would become 0.
Sure.
तो therefore हमें टोटल ये पता है, तो अभी हम इसका नेगेटिव ग्रेविटेशनल फील्ड निकाल लेंगे. एक्चुअल में ऐसा कुछ रहता नहीं है नेगेटिव ग्रेविटेशनल फील्ड, बट जस्ट ताकि क्वेश्चन आसान हो जाए, सॉल्व कर सकें, हम ऐसा एज्यूम कर लेते हैं, या नेगेटिव मास मान लेते हैं, ऐसा कुछ मान लेते हैं. सो देयरफॉर द फोर्स ड्यू टू दिस वुड बी G m2 m upon r, that is 1.5, that is 3 upon 2 r square whole square. Okay. So this small m is equal to m1 upon m2. M2 is equal to m1 upon 8. So I'll just write it down. G m1 upon 8 into 9 upon 4 r square into m. So ये 2 हो जाएगा, equal into G m1 m upon 18 r square.
Correct.
Okay. This is the first two, F2.
Yeah.
So now net force would be the initial F minus the F2. So therefore this will come out to be G m1 m upon r square minus G m1 m upon 18
r square. Correct.
So therefore finally we'll take it 7 G m upon 36 r square. Multiply it by 2, multiply this by 9 minus 2 over here 7. So this is the final expression. So now we have to find it in terms of force, okay, because the answer is in terms of force. So we know that force is Gm1 m upon 4r square.
Correct.
So we'll write it down as 7 f upon 9 into 4. So 9. So this would be the answer.
Right.
So the correct option would be 7f upon 9, A option.
Right.
So using this question we get to know about the concept of negative gravitational field, which is used to find the answers in such cases, in cavity problems.
Okay. Okay, so that helped. We'll get to the next question now. We're on the question number 18th now. You have to choose the correct statement from the given set of statements. We'll start with the first one, and Arnav will explain us whether the statements are correct or not. The first one is, the gravitational and inertial mass are same for all objects. Arnav.
So see, the fundamental thing over here is that what is gravitational mass and inertial mass. So we have got one formula, that is force is equal to G m upon r square into m. Right. And we have got another formula equal to force is equal to mass into acceleration. So in nature, if you think of them as something different, like because of this mass, the gravitational force is changing. Right. If we vary this mass, then the gravitational force will change. And if we vary this mass, then the force, inertial force will change. That is, the rate of change of acceleration will change for different forces. So therefore, they can fundamentally be thought of as two different things. So this is the gravitational mass.
Right.
And this is the inertial mass. Inertial. But surprisingly, in nature, both of them denote the same quantity. That is, the same physical thing is valid for both of them. So therefore, the value of them is also same, the units are also same. So therefore, the first option, that is, the gravitational and inertial masses are same for all objects, is correct. Now coming on to the second option,
which says, at poles, the effect of rotation of Earth on the value of G is the minimum, G being the acceleration due to gravity.
Yep. So we'll have to see the theory behind it, a little bit of it. If this is the Earth and this is the angle with the equator, theta, so the centripetal force is m omega square r cos theta, and this is the mg. So the net force will be the vector sum of both of them. So another cos theta term will come in. So it will come out to be cos square theta. So therefore, as the angle reduces, cos theta's value increases, and as theta becomes 90 degree, it becomes minimum, that is 0 only. So therefore, the option B, that is, at poles the effect of rotation of Earth on the value of G is minimum, is correct, because at poles the angle would be 90 degree and cos theta would come out to be 0. So therefore, its value would be negligible.
Okay.
Now the C option,
which is very massive rockets and extremely tiny molecules, such as the molecules of a gas, require the same initial velocity to escape from the Earth.
This is obviously the correct option, because we know by now that the escape velocity is independent of the mass of the object. It comes out to be 2gm upon r, where m is the mass of the Earth.
Right.
So the term does not have small m, which is the mass of the particle. This is absent. So therefore the third option is also correct. That is, very massive rockets and extremely tiny particles both require the same initial velocity.
Okay, right. Coming on to the D option, D statement. A geostationary satellite, if imparted the necessary velocity, can be put in orbit at any height above the Earth.
For this we have to go into the time period. By now we know that the time period of a particle is proportional to r to the power of 3 upon 2. We know
Right.
we can find it out, like find the velocity first using mv square upon r, then replace the velocity in 2 pi v into r, so you'll get the time
Right.
period. It will come out to be this. So for a geostationary satellite, the time period is 24 hours. So therefore the r also gets fixed. Like you can't arbitrarily put it in any value.
Yeah.
So the value of r approximately is 36,000 kilometers, roughly
Correct.
speaking. So therefore this is incorrect, because it cannot be put in orbit at any height.
Okay. Now the final option. Higher the value of escape velocity, higher the abundance of lighter gases.
This is actually a new concept that has not been taught up till now. So in this, the VRMS is proportional to under root T upon M. It is roughly, I believe, 8 pi RT upon M or something like this.
Right.
So for a light gas, like as gases become lighter, the
Yeah.
mass will increase. So therefore, the mass will reduce.
Reduce, yeah.
So therefore the velocity RMS would increase, because mass is coming in denominator. So therefore for a planet, if the escape velocity is very high, like
Yeah.
V escape is very very high, then this lighter particle might not be able to escape. But if the escape velocity is low, like it is not very high, then there is a possibility that the VRMS of the light gas will be higher than the V escape. So therefore this can escape.
So
Like
is this the same reason that hydrogen can't escape sun, but it does escape?
Yeah.
Earth?
This is the same reason. That is why the abundance of hydrogen on stars is very high. That is like one of
Right.
the reasons, because of the high gravity. So this sums up the question. And
Okay,
you
so
can
the correct options would be A, B, C, and D.
A, B, C, and E.
Yeah.
D is incorrect.
Yeah.
So you can also remember this thing. If it comes directly, you can put it indirectly.
Okay, that helped. Guys, we'll move on to the next question now. So in question number 19, we have been given the distance between the centers of two stars, which is 10a. The masses of these stars are m and 16m, and their radii are a and 2a respectively. A body of mass m is fired straight from the surface of the larger star towards the surface of the smaller star. What should be its minimum initial speed to reach the surface of the smaller star? Obtain expression in terms of g, m, and a. Arnav.
See, it is again a very simple energy conservation question. So we'll have to write the initial kinetic energy and the final kinetic energy and
Right.
equate them, and the potential energy as well. So initial energy should be equal to the final energy. Simplest energy conservation.
Correct.
So initially the energy is due to the gravitational potential as well as the velocity with which it is fired.
Right.
See, so it will be. I'll draw the diagram first. The question becomes very easy after drawing the diagram. This is m1 and 16m, and radius of A and 2a,
2a.
and the distance between the centers is equivalent to 10a.
Right.
Fine. So initial potential energy, it is fired from here. Okay. This is the velocity over here. So initial potential energy will be minus g m into small m. Let's take the mass of this as m, g mm upon r square. So r in this case would be 10a minus 2a. That is 8a. So g mm upon r minus g m into 16m. This would be small m over here upon r. The r would be 2a.
Right.
Plus half m v square. Okay, this is small m over here, just so that there is no confusion. Fine. And this is equal to the initial energy. Now we
Right.
write the final energy. The final energy, when it comes over here, it will be minus G m upon the energy over here would be, the radius would be A, minus G m into 16 into small m upon the distance would be 9m.
Right.
So this is what the most difficult part of the question is, that you have to write these 4 terms correctly. Don't mess it up, don't do any don't do any errors and all.
Correct.
So after this it becomes very easy. So it will come on this side. So finally what we'll get is half mv square should be equal to gm square upon a, 1 upon 8 plus 8 minus 1 upon 16 upon 9. 16 upon 9, okay?
Right.
Half mv square. This is the final expression. So now the calculation part begins. Again, JEE question, you'll have to calculate intelligently.
Right.
So let's start. Let's see what happens. M would get cancelled. This would be m into m actually. So this would get cancelled, the mass of the object which is being fired. Okay. So gm upon a, 8 is 64, 65 upon 8 minus 25 upon 9. So half v square will come out to be this, v square to gm upon a into, we take out 5, so it will come out to be 13 upon 8 minus 5 upon 9.
Right.
So therefore velocity finally would be 1 upon 6 under root gm upon a into 5 into 77. When you multiply this, it will come out to be 117 minus 40.
Right.
So this is what it is. So this is the final answer. So again, it's a easy question. Just write down the terms of energy correctly, don't mess it up, and you will be just fine.